Yeah. Shall I share the screen already, or?
Yeah, you can share your screen. Okay, hello everybody. It's a great pleasure to introduce Michael Schlosser, who is from the University of Vienna, and he's going to talk about basic hypergeometric proofs of two quadruple equidistributions of Euler Stirling statistics on ascent sequences. And today we have a larger audience than usual because some people who attend, some of the students who attend Michael's lectures on special functions have also joined. And also I see Shishuo Fu.
Oh, okay.
And Shishuo is also here. So that's the first time, I think. So it's very, he's a popular speaker, it seems.
Yeah, I invited Shishuo because he's being mentioned in my talk.
I see.
So,
okay. And
I will show some generalizations of work he did earlier with Emma, and Emma is in the audience as well.
So so this is joint work with Emma, Yu Jin, and Emma is also in the audience. So it's very nice to welcome a large contingent from Vienna. And let's begin, Michael.
Okay, thank you very much for the introduction. It's a pleasure for me to talk in this seminar. As I already mentioned, this is joint work with Emma Yu Jin, currently also at the University of Vienna. We're working together and have some results to present, and they partly generalized results which she obtained earlier in joint work with Shishuo Fu, who is also in the audience, and I will come to that later. Because some of my students have joined here as well, I want to give a very light introduction. I want to explain what hypergeometric and basic hypergeometric series are. Please forgive me if this is too elementary for you, but the idea is that these are special functions which have not yet appeared in my special functions class yet, because I've just covered the gamma function and the beta function. And this would be the next step, hypergeometric series. They're built up from gamma functions, say. And then we will apply this series to problems in combinatorics. And in particular, these will concern problems in well, enumerative combinatorics, the so-called statistics on ascent sequences. I will also explain what that is. We will consider distributions and of such statistics on ascent sequences. There will be two statistics or maybe several statistics having the same distribution. We call those then equidistributions. I will also explain what Euler Stirling means in that connection. And finally, we want to prove these equidistributions. They will be reformulated in terms of series, and transformations of series have to be applied to them to prove these results. And that's what will be done in the end here. The problem is also that existing transformations don't work, so we had to find new transformations of basic hypergeometric series to solve these problems. So, as a light introduction, as a prelude, I want to explain what I mean by hypergeometric and basic hypergeometric series so that you get a taste. So let's fix some notation. So n is the set of non-negative integers, positive integers, and 0 non-negative. Okay, the shifted factorial, you should be familiar with that. This is also a Pochhammer symbol, a sub k. This is actually a product of k factors. It's 1, and for k equals 0, so it's an empty product. And for k greater than 0, we have a times a plus 1, and so on. This can be also conveniently written as a quotient of gamma functions. You will only see these gamma functions appearing in infinite series expansions, but not usually in finite ones, because there we just have rational functions involved. But wherever limits are involved, you might see these gamma functions. Just to shorten the notation, I want to write the product of R gamma functions, gamma of A1 to AR as in one notation, gamma of A1 to AR. And similarly with the Pochhammer symbols. Also, I should tell you right away that K could be a negative integer, but we will not need that in this talk today. So we will just have subindexes which are non-negative. What is maybe important, I mean, it's clear that 1 sub k is just k factorial, because 1 times 2 and so on. And it's also good to notice that if you consider a to be minus m, like where n is a non-negative integer, so minus m sub k is 0 if k is greater than m. Why? Because one of these factors then becomes 0. That's easy to see. Okay, so what is a hypergeometric series? So this is a series, just abstractly a series ck for non-negative terms, k greater equal to 0. Normalized, say, c0 should be 1, with a quotient of consecutive terms, ck plus 1 over ck is a rational function in k. So without loss of generality, we can write it in such a form. We have a certain number of numerator factors, denominator factors. We can also have a 1 plus k here. If there's no 1 here, we can put a1 equals 1 to cancel that. So without loss of generality, we can write it in this form. Then the solution, ck, is actually this term, this here. So ck is actually must be then what we have written here. We have a1 up to ar, Pochhammer symbol sub k, 1 b1 up to ds sub k. And so we have r upper parameters, s lower parameters, and this is then a rfs series with argument z. So right now I haven't done much with them, but I just want to show you that they appear frequently, like the exponential function is a hypergeometric series. There are many formulas for hypergeometric series. There's really a lot known about them, and one can treat them algorithmically. We can study them with respect to differential equations and in many other ways. And they appear frequently in combinatorics, where you have binomial coefficients appearing, binomial sums. For instance, in Newton's well-known binomial series expansion, you can rewrite this in terms of hypergeometric series, and it becomes the 1f0 summation, the general one. Upper parameter is a, argument is z, and it sums. It's not difficult to see that if alpha is replaced by minus a and z by minus z, then you can write this as in this form that we have here. A sub k, 1 sub k, the other parameters are not there. Yeah, okay. Just to give you an idea, we will not really need these identities now, but this is just a light introduction. So you know probably the Chukwanov summation. It can be again recast as in hypergeometric notation. It becomes then, with all these Pochhammer symbols appearing implicitly in there, a 2f1 summation with upper parameter a, lower parameter c, and another upper parameter minus m. And because of this minus m, the sum actually just has m plus 1 terms, k from 0 to plus n. The other terms for k greater than m, they vanish. And the right-hand side is just a simple quotient of Pochhammer symbols. So if we replace minus m by b and the 1 by z, we actually have the general 2-at-1 series. This was already studied by Euler. Already gave a hypergeometric differential equation for it, integral representation. And more systematically, it has been studied by Gauss. And this is known to be the hypergeometric function. But nowadays, in the general, one actually considers generalized hypergeometric functions with arbitrary many parameters on the top and on the bottom. But this is the hypergeometric function known as such. And here's now an example with the gamma function. So this connects somehow to my special functions course. So if the parameters is still arbitrary, A, B, and C, the argument is now 1, and the real part is of these parameters satisfies this condition that C minus A minus B, the real part of that is positive. Then this simplifies into this product of gamma functions. Of course, one can go more general, and this is just one more example that there is actually a finite identity here. Because of this minus sign, it truncates from above. And here we have also just a finite product. Although this is much simpler in a way, because it's a finite identity, it can be proved by induction, let's say. Letting m goes to infinity, we recover the Gauss summation. Of course, with this extra condition, which is not needed in the terminating case. Okay, this was just to give you an idea that these appear, and there are many more identities, summations and transformations, where on the left side and on the right side one has hypergeometric series. They are very useful, and they appear throughout mathematics and mathematical physics, so in many problems. Okay, so what is now basic hypergeometric series? This is not as classical. I mean, it still goes back to the classic mathematicians, but it's not as widely known. So instead of the usual Pochhammer symbol, we now have the Q Pochhammer symbol, AQ sub k. Instead of writing it as a quotient of gamma functions, we have now a quotient of infinite products of this form. AQ sub infinity is 1 minus A, 1 minus AQ, 1 minus AQ squared, and so on. So Q should be less than 1 in absolute value, so that this makes sense, so that this converges this product. I didn't write it here. But as a finite product, we don't need Q less than 1. And again, we have for k equals 0, it's just 1, and else we have a product of k factors. We only need k to be non-negative for the purpose of this talk. And again, I use this compact notation for products of Q-shifted factorials. Again, there is if one of the upper parameters, let's say, is of the form q to the minus n, where m is a non-negative integer, then you see here, so if a is q to the minus n, that if you have, at some point, if k is large, you will have a 0 factor. Yeah. So in this case, if you have a sum over k, it will consist only of terms between, up to m, but not larger than that. So these are also called Q analogs of, so the Q basic hypergeometric series. So Q is the base, and that's why it's called basic, not because it's elementary, but because Q is the base. There's a way to recover the hypergeometric series. You haven't seen now the definition yet of a basic hypergeometric series, but they will be similarly composed of quotients of these Q-shifted factorials, so these Q Pochhammer symbols. And one way to get from Q to ordinary is to replace A by Q to the A in here. Then each factor will be of the form 1 minus Q to the something. And if you divide it by 1 minus Q and let Q go to 1, you have A by the L'Hopital's rule. So in a product of k factors, you have to divide by 1 minus Q to the k here, and then take the limit, you recover the usual Pochhammer symbol. So what is now a basic hypergeometric series, or also a Q-hypergeometric series? It's implicitly defined as a series, normalized, such that the quotients of consecutive terms is a rational function known Q to the k. So this quotient can be written as some product of numerator factors, some denominator factors. Without loss of generality, one parameter, the B0, let's say, is of the form Q. And then we have some normalization. We can have extra factors. So because, of course, it's not monic. It doesn't need to be monic or anyway, so we could have other factors as well due to the K appearing. And then some constants there. And an explicit term, so if you solve this simple equation here for Ck with this initial condition, you get Pochhammer symbols for Gk, the numerator and the denominator, and this is the solution now. So a basic hypergeometric series has R upper parameters, S lower parameters, the Q we don't count, and the base Q in the argument set. And why we're studying this? Because there are nice extensions of results for hypergeometric series to Q hypergeometric series. So here's the non-terminating Q binomial theorem. Again, general for a 1 by 0 series, outperformed by A base Q argument set. It simplifies as a quotient of two infinite products. There's the Q Gauss summation. So now the argument is not 1 to make it summable, but C over AB. But if A, B, and C are replaced by Q to the A, Q to the B, and Q to the C, then this is replaced by Q to the C minus A minus B, and then the limit Q goes to 1, it still becomes 1. Yeah. And again, the right-hand side is not a quotient of gamma functions, but now a quotient of these infinite products. So these are nice results. And again, I'm just showing you some finite hypergeometric series formula, which actually extends this one. So if here we let m go to infinity, you see immediately you get this infinite product. And here you have to experience to see that you get this here, but that's also the case. And of course, you have to justify interchanging of limits with summations. Again, much more exists, and you will see some transformation later when it is needed. These are very useful, and they especially appear in number theory, like Q series in general. In the number theory, in combinatorics, in statistical mechanics, and in other areas, like log theory, representation theory. But I will not come to that. I will give you now some application of basic hypergeometric series in enumerative combinatorics. So sorry for the long introduction. Any questions to this point? Because now we will go to the next. Okay, so this is now a different area, and this is now the setup of this combinatorial problem, which you will then see, which will be described in the section on Euler Stirling equidistributions. But the setup is the following: we will consider statistics on so-called inversion sequences of length n. These are abstractly defined, or actually concretely here defined as sequences S1, S2 up to Sn of length n, where Si is between 0 and I minus 1. So we have just one choice for the S1, then with 0, then for S2 with two choices, and so on. So in total, we have n factorial choices of such sequences, and they are in one-to-one correspondence to permutations. Yeah, so we can describe it explicitly. we will not need that here, but we will study actually statistics on inversion sequences. But they can also be understood as statistics on permutations or group elements of some particular group, let's say. Okay, what is a number of ascents is statistic. So maybe, yeah, so there's no real good example here. Okay, so the number of ascents, it means just you look at the neighboring, two neighboring elements, and if you have this relation Si less than Si plus 1, that's an ascent. Else it's a descent, it also will go down. So you take the number of ascents is a statistic, is a certain data of interest we're collecting, yeah, to any inversion sequence. Now, an inversion sequence is an ascent sequence if the number of, if the SI is somehow, if the growth of this sequence is somehow restricted. It shouldn't grow too quickly. So it shouldn't be one more. So SI shouldn't be one more than the number of ascents we had so far in the sequence, if we read it from left to right. Here's an example. So this is, here we have no ascent. Here we have one ascent, so 0, 1. And here's another one. But the 3 is already too large here, because here we had just had one ascent so far in this sequence. So the next number could only be between 0, 1, and 0, 1, or 2, but 3 is not allowed. Yeah, that's a contradiction. Although this is an inversion sequence, because the first entry could be 0, the second frequency 0, 1, and frequency 0, 2, 0, 3. So it's an inversion sequence, but not an ascent sequence. This is a valid ascent sequence of 7, of length 7. Yeah, we have one ascent, another one, here a third one. But this 3 is okay because we had 2 ascents already. Okay. One could think that this is a quite arbitrary statistic and also set with ascent sequences, but they actually appear in naturally in combinatorics. Well, it's not maybe too long ago, but about 10 years ago, Zhicong Lin, Hughes, and Kitaev, they studied them, they introduced them, and they showed that they are equinumerous to other objects. And they established explicit bijections with so-called 2 + 2 free posets, which were already studied by Fishburne in the context of interval orders, so-called 2, 3, 1 avoiding permutations, where this is now a bilingular pattern, 2, 3, 1. And also showed that they're connected to what Stoimanov in 1998 already studied, when he was looking at so-called Vassiliev invariance of knots and regular linearized quark diagrams. The generating function, so is actually what is here. So this is a series expansion, an infinite one in powers of t, and the coefficient of t to the n gives exactly the number of these ascent sequences on n letters, yeah, at length n. Already Zhicong has found this generating function, and Busquet-Milou, and co-authors, they have done this independently at a little bit different means, using the kernel method. But Zhicong already showed that this is the generating functions of this sequence of numbers which Fishburne came across. And this Fishburne sequence, here are the first terms. It starts with 1, then 2, 5. There's no explicit formula known for them, but they are slightly higher than the Catalan numbers. which would start with 1, 2, 5, 14, 42, and so on. But of course, less than n factorial. So, which would be 1, 2, 6, 24, and so on. Of course, because we have just certain permutations are allowed, not all. So we expect the number to be smaller than n factorial. Okay. So dealing with these Fishburne numbers is difficult because one needs to deal actually with a generating function, which looks also a bit complicated and strange here. Okay, let me continue now with certain other statistics defined on inversion sequences. They will show up in these Euler Stirling equidistributions. So the most important one was, let's say, the number of ascents. Maybe it's not the most important one, but the one we started with, because we could immediately see that they, we could analyze properties and see that they are connected to these Fishburne numbers, which Fishburne has studied, and so on. Other statistics are here. Reps is not the Republican, so it's anything like that. The reps are here. Rep is the number of repeated entries. So we'll see some example, I believe. Yeah, so let's take this sequence here. The number of repeated entries is 2 of the sequence because the 0 appears twice and the 1 appears twice. Yeah. Multiplicities counted as well, but there are no higher ones than 2 here. Okay, then 0 is the number of zeros. We have 2 zeros appearing in this specific sequence. Max of S is the number of occurrences which take of SI which take their maximum value. The maximum possible value would be I minus 1. So 0 is maximal. That's always there. The next entry could be between 0 and 1, but it takes 1, so it's also a max here. 2 is this max, and so there are just these 3 maximum values. So max of this sequence S is 3. Then R min, sorry, the ascent I didn't count. So here's an ascent 1 between 0 and 1, and 1 and 2, and 1 and 0 and 1, 1 and 3, 3 and 5. So there are 5 ascents. And R min is now the right to left minimum of S. So we read it from the right. We see how far how long do we go downwards. So 5, 3, 1, 0. This number is 4, and then it goes up again. So this is 4. Yeah. You see these seem a bit random, but Fouata, Dominique Fouata, 1977, actually established a result from which one can get this result as a consequence. So the distribution, if one sums over all inversion sequences now, not ascent sequences, U to the power of ascents of S, X to the power of repeated entries of S. This series is symmetric in U and X. Yeah, so that's what we. So this is an equidistribution, a symmetric one. Also, if X is 1, let's say, so let me go back here. If X is 1, it means that the distribution of the inversion sequences with respect to the ascent sequence statistics has the same distribution with respect to the repeated entry statistics. Or if U equals 1, you see the same. Yeah. So there's no thing there, but okay. Now it turns out that this equidistribution, which is quite elegant and
hi Michael, can you speak a little louder?
Yes, of course. I can try to speak louder. Yeah. Do you hear me well now?
Yeah, it's better if you're louder.
Okay, I'm sorry. So it turns out that this equidistribution not only remains true if we sum over the smaller subset, AN instead of IN, so ascent sequence instead of inversion sequences, but one can even generalize by having more variables involved and further statistics. And actually this was conjectured by recently in a preprint appearing first in 2018 in joint work of Shishuo Fu is also in the audience, Emma, Yu Jin, who is also here, and of their co-authors Lin, Yan, and Zhao. The paper was published in 2020 in JCTA, and they conjectured this equation, so this equidistribution. So now we have four, so this is a quadruple equidistribution, which yeah, we're already in this section on Euler Stirling equidistribution. So these are four statistics: ascents, repeated entries, zeros, and maximal entries. And here we have the same variables involved and the same statistics, but connected with other variables. So it's bisymmetric because if u and x get interchanged and z and y at the same time, we have equality. Yeah? If we only interchange two variables, we don't have equality, at least not from this equation here. So what is now Maclaurin or a Stirling statistic? This is just a matter of naming something. So any sequence with over ascent sequences, which has the same distribution of as the ascent statistics, is called an Maclaurin statistic. And any sequence which has the same distribution over all ascent sequences as the zero statistics is called a Stirling statistic. I'm just rewriting this one more time. So this is just this equation here, just so that we don't have to memorize it. So ascent sequence and, is anyway Maclaurin by definition, and rep is another Maclaurin statistic because it's set and y is 1. And x is 1 as well. We see that ascent distribution is the same distribution as the repeated entry distribution. And similarly, if because 0 is a Stirling statistic, max is also 1 because if u, x, and y is 1, then only the set survives, and we see that max and 0 have the same distribution. Okay. There was also another statistic, right to left minima. That's a Stirling statistic. There are different ways to see that, but one way to read it off from a equidistribution result is taking this result by Fu, Jin, Lin, Yan, and Zhao, which gives which is actually similar to what they conjectured here. But this is not symmetric because there's this R min involved, which is just on the right-hand side, but not on the left-hand side. That's quite remarkable as well. Okay. Now in this new joint work with Emma, we've shown a symmetric quadruple equidistribution, which involves this R min statistic and the max. So the 0 is not involved, the 0 statistic, but we have 4 statistics from these 5. We also have other results proved with more statistics in our paper, but in terms of basic hypergeometric series, we just want to restrict now to quadruple equidistributions. So now one could ask how to prove this result. And also we are able to prove, let me go back, this result, which was conjectured by Yu Jin, Lin, Yan, and Zhou. And with help of basic hypergeometric series, we can give a proof of this result. So the idea, of course, is to reformulate this in terms, one side, in terms of basic hypergeometric series, and then to show that the symmetry holds using some fancy, let's say, identities of basic hypergeometric series. So that's the idea. And for that one needs, well, actually, we don't, so it was not like that we recast really the left-hand side, but the generating function. So it's a bit more, there's a step in between. So actually, what do we mean by generating function? So this was already done now by Yu Jin, Lin, Yan, and Zhou. They gave the generating function for this sequence here. So this was for this distribution involving rep, max, ascent, and zero. Let's see whether that appears. It appears here. Yeah. So for the left-hand side, if you multiply this expression by t to the n and sum over all n greater or equal to 1, they were able to show that this, I don't want to say it simplifies, but it equals this series expansion. M greater or equal to 0, then you have certain factors in the numerator denominator. And here also factors. And if you look closely, you see already that this is actually can be written in terms of Q polynomial symbols, where Q is 1 minus R here. Yeah, we will come to that later. But also the R is complicated, and it's a product of other factors, of other variables, let's see. We will not attempt here to derive this. There was some kind of combinatorial. I just want to describe it in words, and also for the next result, which in our paper we were able to establish. The idea is to use some combinatorial decomposition of ascent sequences and to obtain recursions for the generating functions for them, and they were then, and then to solve these recursions with the help of the kernel method, iteration, and then to find these explicit series representations for these generating functions of these distributions. So this is now an analogous result. This is generating function for a distribution with rep, max, ascents, and R min now involved. And you see that this appear, I think it, no, here is the 0, so it appears on this side here. Okay, so we have this quadruple distribution appearing here, and we have symmetries which we want to prove. In one way, we had this is a new result. This was conjectured the second way, the bisymmetry. And we can also prove it by using basic hypergeometric series. And the idea is now to prove it on the level of generating functions. So to simply, because as I already mentioned, these series are actually basic hypergeometric series, so it still has to find the substitution of variables and to really write it in terms of basic hypergeometric series, to identify it in that way, and to use the right theorems. But then here it's easy. You see that you have some symmetry which you want to prove. That would be the first result. So symmetry in replacing y and v. And the second is now a bisymmetry. we replace x and y at the same time. No, so x and u and y and z. Yeah. So this is bisymmetry. You have to replace both at the same time. Then you have equality. So that's the idea. And we will, as I already mentioned, apply suitable transformations of basic hypergeometric series. So any questions to this point? Okay. I'm just recalling what a basic hypergeometric series is. So because of the R and the S already taken, I now have alpha upper parameters and beta lower parameters. Yeah, as in my definition of as a alpha phi beta basic hypergeometric series. And what we want to use is this transformation now. So this is a 4-3-3 transformation, which I haven't shown you before. This is above the Q-Saussure summation. And this is a terminating identity by Sears. So because of the q to the minus n, we just have actually n plus 1 terms involved on each side of the series. So k runs from 0 to n, but the other terms all vanish. But actually, we're dealing with here, these are actually infinite series, and here also. So the question is what to do. The other thing is that if we're dealing with infinite series, usually in basic hypergeometric series, we extend them in terms of base q. We usually want q to be less than 1 in absolute value, and consider analytic expansions around q equals 0. In the Fishburne combinatorics, let's say, very often you have generating functions in base, which can be also written in terms of basic hypergeometric series and q Pocholo symbols, but the base here is q equals 1 minus r. Yeah, as you've seen here. So sorry, 1 minus r I, which is increasing from 0 to n here, yeah, and here as well. So this 1 minus r appears frequently, yeah, but we want to expand it. So the r is t times something, and this is a generating function t around 0, yeah. That means that r should, we want to expand this as a function r around 0, or if we replace r by 1 minus q as a series in q around 1. That's a bit complicated, let's say, or tricky. But that's what we're doing then, and we require this result, and this is like a master result from which we can then prove the other two equidistributions. So this is more general than what we need, but this is what we can get from the Sears transformation without much extra work, let's say. Okay, so let me just analyze this here. So A, B, and C, and D and E are arbitrary parameters, but they should not involve, they should be independent of R, well, not necessarily dependent. They should not, there should be no vanishing constant term in R in this series, because we actually we want to expand this in powers of R here. Okay. We'll also interpret this as power series in A and R, so it actually is double series. What we have here is a 1 minus R to the Q, to the J, but think of this 1 minus R as a Q. So base Q everywhere, but we expand it in around Q plus 1. And this Q to the J does not make the series truncate. So this is really an infinite series. Yeah. But because of this, let's say, integer power of certain parameter here, this product here in front of this infinite series becomes a finite product. And that's the important part. So this is not a quotient of gamma functions, but it's actually a rational function. Because that's where we really would have problems having, considering q tends to 1 or so. We would have gamma functions involved, q gamma functions, or infinite products. But with finite products, that's not a problem. On the series, there's no problem to expand here. So that's maybe an idea. Here's the proof. I will probably just say a very few words. I will not go through it in detail, but we expanded, as I said, in powers of A and R, and really observe that the contribution of new terms to each fixed A and L is finite. So even in a combinatorial meaning, or in the meaning of formal power series, this expansion makes perfect sense. Okay, and now there's the analytic part. Okay, so both sides agree for, so it's analytic in A, and both sides agree for A equals 1 minus R to the minus n. In this case, this factor 1 minus A, which you see up here, becomes 1 minus R to a negative integer. And then it becomes a 433 as we have here. And then we can prove this identity by the Sears transformation. Okay. And of course, this is true for n equals 1, 2, 3, and so on. And it accumulates at minus infinity, which is also a point where the identity is true. And so the identity is true for all A in its domain of analyticity. And if you're a little bit worried if it's really correct, this identity, we have expanded this identity in powers of A and R to arbitrary order, or to certain order. And so we have checked it numerically, let's say, on the computer. So it is correct. Okay, now new results can be obtained. I mean, let's say special cases can be obtained which are useful. We are going now in two directions. So if A is 1, it simplifies considerably. If A is 1, we have a 0 here. That means the order drops down by 1. And a 0 here as well. So we get 3p2 transformation in that case, which is useful to prove one of the transformations which we need. And the other one is by taking a different limit. Again, we get rid of one parameter, but not by a confluent limit. Replacing C by D over C, taking D goes to 0. The main difference here is just that we have one quotient of U comma symbols here, and here we have 2 of them here. But again, this is not a mistake, and these two transformations are not equivalent to each other. Okay. Maybe also interesting to notice that this is an infinite series, but the argument is the same as the base, 1 minus R here, which is already different than at the Q-Gauss summation, let's say, where you would have C over AB. Yeah. So here you have really argument, the base. But it's expanded around R. Yeah. R equals 0. Yeah. Yeah. power series in R. Okay. Now you should just trust me that the symmetry. So remember that one of these generating functions, maybe I'll just show you them again. They're both very similar, but this series can be rewritten in a form so that the transformation which we want to prove becomes this transformation here. A certain series which is now written with Q Pochhammer symbols, with one upper parameter, another one. Down here we have also two. Someone can wonder what happened to the third parameter if we want to apply the 3phi2 transformation. I can just taking j equals 1, because there's a 1 minus r appearing here as well, which is somehow hidden. So the base is always hidden as one of the lower parameters. So we're applying the j equals 1 case of one of these corollaries with a certain substitution of variables to make the series being equal to the left-hand side. And we already put things to the other side so that this transformation actually corresponds to the basic hypergeometric series transformation. Okay. You see maybe here that the two series are symmetric. You replace y by v, yeah, you get from one series the other. And also the role of these two factors gets changed by replacing y by v. Okay, this shows the symmetry, and now the bisymmetry is just another identity. Can be now rewritten in this form. Now we have one Pochhammer symbol here, two here, and one linear factor. But that can be written as a quotient of two Pochhammer symbols, of two adjacent ones. So again, j equals 1, and we have then a different specialization of the variables a, b, c, and e, and that establishes the bisymmetry. Now, more results exist, of course. I mean, we have worked out explicit bijections. So, because this proof is very analytic, one could say, it's or algebraic manipulations of generating functions and then finding formulas for these generating functions. So it has a strong analytic flavor. Combinatorialists, they usually like bijections, so we also have bijections. We have even some far-reaching generalization of some of the results, which concerns a septuple equidistribution. And then we conjectured, we have proved a bisymmetry for them, but the proof so far is combinatorial. And on the level of generating functions of basic hypergeometric series, we have not been able to find the proof or find the right identities needed for that. So there would be larger identities, presumably. And if you're interested, you might look at this preprint, which is on the archive. I forgot to write the number, but at the archive, but you can find it by Googling it, or it's on the homepage. We also have a conjecture about the symmetric quintuple equidistribution on inversion sequences, so not on ascent sequences, but on inversion sequences, which corresponds to permutations. So thank you for your attention. Any questions? Remarks?
Questions?
there are no questions, I will stop sharing the screen so that we can go in gallery view.
Yeah. Right.
So, Michael, I had one question.
Yes.
So, you said that the generating function is related to that of Fishburne numbers. So, you have
Yes.
the Zagi is QQ sub k, summation k going from 0 to infinity.
Yes. Yes.
So, there is another identity which appears in Zagi's paper, which is relating it to I forgot some kind of some kind of transformation for that series. So in the topology, the paper which appeared in topology journal, Zagi's paper. So I was thinking if in this more generalized situation, you said you have this more generalized identity. For the 3p2, do you get such further identities of the type that Zagi has? So, sorry, I don't remember exactly.
Yes, so I'm not sure. So I haven't studied in detail now. I know that the work of Zagi has been, from a basic hypergeometric point of view, been studied and extended by Jelinek and George Andrews. Yeah, so they might have done things there which you're mentioning. I'm not sure. And
okay.
We have used some techniques from that paper, in particular viewing the series as a power series in A and in R. That technique was used by Jelinek and Andrews and Jelinek, to get something more general. And I've tried to, we have tried to get to use as general. The transformation which we derived, this 4p3 formula, is more general than what is needed here.
Yes.
And I'm not sure if the full power can be used to prove more results. Yeah? But that might be interesting.
It's nice to see how the same generating function has so many combinatorial interpretations, like the Fishburne numbers and the ascent sequences.
Yes.
More interval orders and
beautiful. Yeah, that's surprising as well. Yeah.
Nice talk.
Okay, thank you.
Any other questions or comments?
I just wanted to ask, Stirling numbers are associated with Bell polynomials also. So do you use them also?
No, I'm not. So I'm not analyzing Stirling numbers, but we just called a certain distribution to be a Stirling distribution. I actually don't know the history of this. I don't know why it's called Stirling distribution. It might have been considered by Stirling in some context.
Okay.
Yeah, but we're following the conventions of other people. So there's something called Mahonian. Mahonian distribution on permutations. That's just something similar, where you have inversion statistics or the major index and other statistics which are equidistributed. And in the context of ascent sequences, a similar role is played by these Erlang statistics and Euler statistics and by the Stirling statistics. So that's.
Thank you. Thank you.
Okay, if there are no more questions, let's thank the speaker again for a very nice talk. I'm seeing a lot of messages on the chat saying that there's a very nice talk, Michael.
Okay,
wonderful,
thank you
wonderful.
For your nice comments, and was nice seeing you.
Okay, so I'm going to stop recording now.